Hello! Today, we are not just going to talk about a software topic, but about how machines see the world known as computer vision. During the video, we will take a look at how pixels are transformed into meaningful data and the mathematical architecture behind this vision capability. And most importantly, we will address the other side of the coin, namely the security and challenges aspect, by asking the question, how secure are these systems really? For the human brain, seeing is an action that begins at birth and requires almost no extra effort. However, for a computer, it's a highly complex process and very different from human vision. Computers don't see images, images are just numbers from a computer's perspective. To keep the math simple, let's assume we are looking at a black and white image. In this case, for a computer vision, a cute cat or a nature photo is a huge matrix of millions of integers ranging from 0 to 255. Here lies the biggest problem that computer vision is trying to solve: semantic gap. With just a slight decrease in lighting, the matrix of numbers seen by the computer changed completely. The image is now a completely different image for the computer. However, we still see the same cat. That's why we need to teach computers to extract meaning from these numerical matrices. They need to understand, not just look. In this video, we will dive into the background of this process, from processing raw pixels to convolution neural network architectures, and from object detection to face mesh technologies. We will also explore the evolution of computer vision, uncover its hidden vulnerabilities. Welcome to the world of computer vision. Let's get started. Computer vision has evolved through failures, just like every technological leap in history. From the 1960s to 2010s, engineers tried to achieve results by writing rules by hand, and they called these handcrafted features. If the computer saw two triangles side by side and a mustache in the middle, it was told to recognize it as a cat, and progress was made in this way. However, the biggest problem with this approach was that real life didn't have such clear-cut rules. When the light changed or the cat turned sideways, the computer produced incorrect outputs. But in 2012, not that long ago, everything changed. AlexNet took the stage at the ImageNet competition and reduced the error rate to an unseen level. For those unfamiliar, ImageNet is a dataset created to train and test computer vision models containing over 40 million labeled photos. AlexNet, on the other hand, is a convolutional neural network, also known as CNN architecture, that won the ImageNet Large-Scale Visual Recognition Challenge 2012 by a wide margin using the ImageNet dataset. It demonstrated the power of deep learning and GPUs. So, what was the reason for this difference? What was CNN doing differently? The answer to this question was, of course, nothing more than pure mathematics in the background: convolution. As you can see on the screen, the mathematical formula for convolution may seem like an unfamiliar term and mathematically challenging, but the logic is actually very simple. Let's look at this handwritten digit on the screen. To understand what number this is, the convolution doesn't look at it all once like we do. Convolution scans the pixels of this number using filters, also known as kernels. These kernels slide over the image, pixel by pixel, and perform a mathematical multiplication operation. The aim is to capture specific patterns: a horizontal line at the top, a curve at the bottom, or a vertical stroke. The first layers learn only these simple strokes, but as the network becomes deeper, these lines merge to form loops and curves, and finally the complete digit. In other words, the computer learns to see by going from parts to the whole. We don't define what a number is, it extracts the characteristic of the number by analyzing thousands of handwritten samples. This is the difference between handcrafted features and feature extraction, and this is where AlexNet's record-breaking difference comes from. Rather than writing rules for the computer, we enable the computer to learn the rules. We talked about architecture, convolution, and filters, but there's a missing piece in this puzzle. How does the computer actually learn these features? It doesn't happen magically, it happens through a process called training and backpropagation. Imagine the network makes a guess. It looks at a cat photo and says, "This is a dog," but the label says cat. The computer calculates the difference between its guess and the correct answer. We call this mathematical difference the loss function. Then, A fascinating process called backpropagation begins. As the name implies, the algorithm propagates the error backward through the network, from the output layer all the way to the input. It adjusts the millions of parameters, also known as weights and biases, in the layers we mentioned earlier, effectively saying to each connection, you caused this error, change your value slightly. This happens millions of times for millions of images. It's like descending a foggy mountain, the algorithm takes small steps downwards to find the lowest points of error. This continuous optimization process is the real engine that powers a CNN. Without this learning mechanism, a CNN is just a lifeless mathematical structure. Now we understand the maths behind the learning. Let's take a look at what we can do today with these capabilities. To understand the true power of computer vision, we can categorize its main tasks into three layers of intelligence: seeing, understanding, and acting. It starts with simple recognition, moves to spatial awareness, and finally to complex behavioral analysis. Let's break them down, starting with the most fundamental one: image classification. As the name suggests, the task aims to answer the question, what's in this image? But the answer is not just a binary yes or no. The model works with probabilities. When a computer looks at an image, it produces a confidence score. It might say, I am 90% sure this is cat, 9% sure it's a dog, and 1% sure it's a car. Understanding this score is crucial because in real-world applications we need to set a threshold. If the confidence score is more than 50%, maybe we can trust the model's decision at all. However, the real world is not limited to a single object. A photo can contain a cat, a dog, and a car all at once. This is where object detection comes into play. The question changes to where are the objects? Models like the famous You Only Look Once, also known as YOLO algorithm, are game changers here. Unlike older algorithms that scan the image piece by piece, YOLO looks at the entire image at once and predicts all the bounding boxes simultaneously. This speed is what allows computers to detect objects in real-time video, not just static photos. But detecting an object is not enough. Let's analyze this example video. We need to know that the car in the first second is the same car in the fifth second. This brings us to a subtask called object tracking. Algorithms like deep sort take detection one step further. They assign a unique ID to each object. So, even if objects cross each other or get momentarily blocked, the computer remembers this is car ID 1 and this is car ID 2. Without tracking, a video is just a chaotic sequence of unconnected detections. We know what the object is and where it is on the screen, but screens are 2D and the world is 3D. We are missing a crucial dimension: depth. This is where monocular depth estimation comes in. Humans use two eyes to perceive depth, but advanced computer vision models can now predict distance using just a single camera. The model analyzes the size, texture, and perspective of the objects to create a depth map. In this map, closer objects appear brighter and distant objects appear darker. For an autonomous vehicle, knowing that an obstacle is 50 meters away versus 5 meters away is the difference between gently slowing down and slamming on the brakes. Sometimes, drawing a rough box is not precise enough. We need to know exactly where an object starts and ends at the pixel level. This is where segmentation comes into play. Let's look at the evolution of this technology. First, semantic segmentation. This paints every pixel of a certain class with the same color. As you can see here, all people are red and the grass is green. It understands the environment perfectly. But there's a flaw. Look at the players hugging. The model sees them as one big red blob. It knows they are people, but it can't tell how many people are there. To solve this, we have instance segmentation. It goes a step deeper and distinguishes between individuals. It says, this is player A and this is player B, painting them in different colors even if they overlap. This is critical for counting objects or robotic grasping. But did you notice something? We lost the background. The grass and sky are ignored. So, is it possible to have it all? Yes, this brings us to state-of-the-art, panoptic segmentation. It combines the best of both worlds. It understands the background context from semantic segmentation, and it distinguishes individual objects from instance segmentation. This gives the computer a complete, pixel-perfect understanding of the entire scene. Panoptic segmentation gives us a pixel-perfect understanding of the world, but it treats a person as a solid blob. It doesn't understand biomechanics. This is where pose landmark detection comes into play. Segmentation outlines the shape, but it ignores the structure. Pose landmark detection goes deeper. It maps the human body not as a flat surface, but as a digital skeleton connecting critical key points like the nose, shoulders, elbows, and wrists. We see this technology in action every day. It's the magic behind social media filters that lock a mask onto your face perfectly. It's also how modern cars detect driver fatigue by measuring if your eyes closing. But beyond that, it enables the machine to understand detailed geometry. This is exactly what's happening in my demo right now. Look at the green mesh covering my face. The system is tracking hundreds of distinct landmarks in real time. It doesn't just see a flat image. It captures the precise structure and movement of my face instantly. But let's take it one last step further. We have the skeleton, but is the person walking, running, or playing tennis? This is action recognition. By analyzing how these key points move over time, the computer understands context. This is the difference between the camera seeing a person and seeing a person doing push-ups. Up to this point, we have talked about the computer as a passive observer. It looks, it detects, and it understands. But the final frontier of this evolution is creation. This is generative vision. If a CNN can distill an image into a label, what happens if we reverse this process? Can we give it a label and ask it to dream up an image? The answer is yes. Models like Stable Diffusion use the patterns they learn to generate new, never before seen images. They understand the visual world so well that they can now replicate it. This creates a complete loop, from seeing to understanding and to acting, and now it takes us one step further, to imagining. We just explored the amazing potential of computer vision, ranging from real-time tracking to generating entirely new worlds. However, these systems are not invincible. People generally believe that machines are perfect. However, from a security perspective, these systems are quite vulnerable. It's difficult to deceive a human, but to deceive a CNN model is not. The image doesn't even need to change completely. With just mathematical noise, the model begins to lose its ability to recognize what it sees. Let's see this situation live and understand it better. I'm adding mathematical noise to my camera right now. The image may be a little bit blurry, but you can still see me clearly and recognize me. I am still here for the human eye. But computer vision is currently blind. Look, I am physically here. The lights are on. My face is in front of you. However, because of the invisible noise we added to the pixels, the computer sees me not as a human, but as a meaningless bunch of data and ignores me. This may only be a minor demo, and the full extent of the problem may not be fully understood. However, when it comes to autonomous vehicles, these issues can become life-threatening problems. So, are we completely helpless against these threats? Fortunately, no. Just as biological viruses have vaccines, computer vision models have adversarial training. Engineers intentionally generate these noisy images and feed them into the model during the training phase, labeled correctly. We essentially say to the computer vision model, don't be fooled by this noise, this is a still stop sign. By exposing the model to its own weaknesses, we make it robust. It's an endless cat and mouse game between challenges and computer vision models, but it's the only way to secure the future of computer vision. Finally, let's talk about the silent threat, bias. Unlike the noise we just saw, this is unintentional, but equally dangerous. CNN models rely on patterns that appear often. If 95% of your training data consists of sunny days, the model optimizes itself to recognize those conditions perfectly. But this creates a long-tail problem. The rare 5% like a chaotic accident or blizzard are treated as anomalies and ignored. This leads to a critical failure called domain shift. Imagine a self-driving car trained mostly in sunny California. It learns that roads are gray and lane lines are white, but if we deploy this same car to Canada in winter, the road is white with snow and the lines are invincible. The model fails not because the architecture is broken, but because of its definition of reality was too limited. So, how do we solve this? We cannot wait for years to capture every possible storm or rare event on camera. This is where a new solution emerges: synthetic data. Using hyper-realistic game engines, we can take that sunny road and instantly change the conditions. We can simulate different situations from a sunny day to heavy rain or total darkness. But we don't stop there. We can also simulate dangerous edge cases that are impossible to test in real life, like a deer jumping onto the highway or chaotic accident scenarios. By doing this, we fight bias with generated reality, ensuring the model has seen every possible scenario, from the darkest night to sudden accidents, long before it happens in the real world. Today, we started with the mathematics of pixels and explored how CNNs learn about the world. We understood systems that recognize our faces, but we also saw how they can be blinded by a single mathematical noise. Computer vision is no longer a science fiction fantasy. It's a concrete reality that has entered our lives. However, as we have seen in the demo, it's not still perfect and has a long way to go. These systems are currently excellent co-pilots, but making them a true autopilot that's bringing them to a level of safety where we can fully entrust human lives to them is in our hands. The computer vision systems of the future must not only see, but also understand when they cannot see and never make mistakes. Thank you for watching.